Assalamualaikum. Today our group E1 will present about piping system. Here is our group member consists Putri, Azrin, Shaza, Farisha and Adi.
Assalamualaikum to Dr. Zazarin. My name is Putri Andriana Bitiaziza. I will start with the part of introduction. Today we'll be discuss the design of critical water supply system for the construction of new faculty mechanical and manufacturing engineering FKMP building at University Tun Hussein on Malaysia. So this project led by Southern Engineering and Construction Sdn Berhad requires an efficient piping system to pump water from Lake G3 to a storage tank elevated 10 meters above ground level. The system met a minimum flow rate requirement of 0.01 meter cubic per second while ensuring optimal performance, reliability and cost effectiveness. Our focus is on applying key principles of fluid mechanics to analyze internal pipe flow, evaluate energy losses and select appropriate system components for this piping system.
Next is related theory. So basically, the piping system that we have designed is to transport the lake water from G3 to a FKMP construction site. So basically, in this system design, we have applied a few of fluid mechanics principle to get an efficient pipe system design. So basically, we have like a few key analysis that we conduct, such as flow type, energy equation, losses, pump power and MPSH. So I will go through one by one the equation related theory that we have used in this design system. First and foremost, the related theory equation that we have been used is energy equation. So it relates to pressure, velocity, elevation and also pump energy, which also includes energy losses because we want to ensure the reliable and sufficient in the pump system. So the equation used is P1 over rho G plus V1 square over 2G plus Z1 plus head pump is equal to P2 over rho G plus V2 square per 2G plus Z2 plus head loss. Next is continuity equation, which it is based on mass conservation, which the equation is Q is equal to VA, which V can be determined by rearrange the equation, which is Q per A. Next is Reynolds number. So basically Reynolds number determines the flow type, whether it is laminar flow or turbulent flow. So we can use an equation of which is Reynolds number is equal to rho VD over mu, which mu is dynamic viscosity. The Reynolds number is less than 2100. So it is laminar, but then if the Reynolds number is above 4000, it is turbulent flow. Next is about major losses and also minor loss. So as we know, is in energy equation, it has involved the head loss in the equation. So we need to find the head loss in major and also minor. So for major loss, it is caused by the friction in long straight pipes, which we need to determine by using equation of HL is equal to F times LV square per 2GD, which F is a friction factor, which determine the flow is laminar. You can straight using F is equal to 64 per Reynolds number. But then if it's a turbulent flow, we can use either Moody chart or Colebrook-White equation. But then for minor losses, it caused by a few things, which is valves, elbows, joints and so on, which can be determined directly by using HL minor is equal to KL times V square over 2G. After we have determined the head loss, the related theory in energy equation knows that we need to find the head pump. So head pump represents the energy added by the pump, which we know if the pump head is higher, the pump can overcome a greater elevation of or friction losses. So basically, head pump can be determined by using Z2 minus Z1 plus HL, which is HL have been determined by using the equation of HL major plus HL minor. Next, we can determine the required power. Required power is that where we want to know the power that received by the water during the piping system. So it can be determined by using a required power is equal to rho GQHP, which is rho G is the density based on the lake water and also Q is the volume flow rate that have been conducted in the theory, which is 0.01 meter cube per second. Also heat pump, which have been determined in the equation of heat pump. Next, to ensure the pump can move water through the system effectively, we can determine the estimated power of pump by using the efficiency equation, which is efficiency can be determined by the chosen of pump we use in catalog. Theoretically, so we know the efficiency of pump is equal to required power per pumping power. So we rearrange the equation, we get the estimated power of pump is equal to required power per efficiency of pump. Last but not least, to prevent any cavitations during the piping system that can be damaged from the vapor bubbles, we need to determine the net positive suction heat, which is NPSH, to ensure more safety and efficiency during the pump operation. So NPSH is equal to suction pressure per rho g plus V square per 2g minus the vapor pressure over rho g. And that is all about related theory in this piping system design.
My name is Azrin Shazul binti Azari. My material number is CD230151. The purpose of this system is to transfer water from G3 lake to the FKMP construction at University Tengku of Malaysia. It is designed to support construction activities such as concrete mixing, cooling and site cleaning. This system consists of several key components. The centrifugal pump acts as a main pump, ensuring a steady and continuous flow of water from the lake to the site. HDPE pipe and elbow are used to carry water throughout the system, despite a corrosion resistant and flexible, making them suitable for directional change and long-term use. A gate valve. A gate valve is included to control or completely stop the flow of water when necessary or emergency situation. The suction hose made from flexible PVC connect the pump directly to the lake, allowing smooth water intake into the system. Water is stored temporarily in the water tank, which is placed at an elevated position. This allows water to be distributed to the construction site using gravity without the need for additional pumping. To prevent overflow, a floating valve installed into the tank. The valve automatically stops the water inflow when the tank is full, ensuring safe and efficient water management without the need for manual intervention. Overall, this system is designed to be practical, efficient and reliable for continuous operation on site. This slide presents the main component used in the water piping system design for the FKMP construction site at UTHM. Each component has been carefully selected to ensure durable efficiency and low maintenance. First, we have centrifugal pump, model SEN 40-200A with a power rating of 10 horsepower and a total height of 57.7 meters. The pump serves as the primary device that moves water from the lake to the construction site efficiently and continuously. Next, we have the water tank. The water tank made from polyethylene. It has a capacity of 1,820 litre or 400 gallons and its dimension are 1,524 times 1,524 times 1,092 milliliter. The tank temporarily store water and allow gravity feed distribution to different parts of the site. This system use HDPE pipe which have an outer diameter of 75 mm and the inner diameter is 65.4 mm. Each pipe is 10 meter long and has a wall thickness is 4.5 mm. Despite are chosen for their corrosion resistance and strength. A gate valve size of 75 mm and made from PVC is it installed to allow flow control and shut off during maintenance and emergency. Pipe elbow are used to direct water flow according to the layout of the site. They are made from HDPE and come in angle of 45, 60 and 90 degree with a diameter range from 31.75 to 75.5 millimeter. And the suction hose made from flexible PVC has a diameter of 31.75 millimeter or 1.25 inch. It connect the pump to the leg and allow easy water intake with minimal installation effort. Lastly, the system include a float valve with a ball that's made from the brass and sized at 25.4 millimeter or 1 inch. This component automatically stop water inflow when the tank is full, prevent overflow and ensuring efficient water management. Together, there's a component from a reliable, efficient and cost-effective piping system that support the water needs of the FKMP construction project.
In the figure labeled as piping system layout is the proposed piping system. The diagram outlines the system's main components, including the lake's water intake point, centrifugal pump, pipeline flow, and structural connection between buildings and landmarks. The schematic demonstrates how the pipeline avoids obstacles and maintains an efficient path, incorporating directional transitions to accommodate elevation changes and topographical restrictions. The schematic is crucial for component specification, hydraulic analysis, and true planning. Next, the detailed plan view of the proposed piping system illustrated in figure labeled as detailed plan view of piping layout provides a more accurate representation of the system's spatial arrangement and physical layout. It shows the pipeline's path, suction line, and discharge line with strategically placed pipe fittings to minimize head losses and optimize flow. The figure also provides precise estimations of pipe length, aiding in hydraulic calculations and construction planning. The tank's placement aligns with flow direction while maintaining safety for maintenance and expansion. Not only that, this proposed pipeline structure can be verified using a satellite map view, providing a realistic interpretation of the schematics. This imagery helps bridge the gap between schematic planning and execution, ensuring the pipeline route works well with existing infrastructure. The satellite image also aids in making decisions about safety zoning, pipe trenching, and pump placement. It also aids in estimating elevation profiles and horizontal distances. This satellite reference strengthens the proposal's credibility.
Alright, so now we in calculation part. So first thing first, in this part, we need to find the Reynolds number. So since we have two different pipe, which is HDPE pipe and then suction hose pipe, and the different diameter also, so we need to find the velocity for each pipe. So when we get the value of velocity, so we can calculate the Reynolds number. So after we calculate the Reynolds number, the value of Reynolds number that we get is above 4,000. So it means the flow is turbulent flow. So when the flow is turbulent flow, we need to use Moody chart to find the friction factor. So in friction factor, we need to find the relative roughness first. So to calculate the relative roughness, we need to find surface roughness. So in this case, the surface roughness is have a same value, which is 0.0015 millimeter. So after we get the value of relative roughness, we can find the friction factor by using Moody chart.
After the value of Reynolds number and relative toughness for both HDPE pipe and PVC suction hose, we can obtain their friction factor by using Moody chart. As we can see in the figure, we can see that friction factor value can be easily obtained by using Moody chart. The Moody chart offers a graphical method to determine the friction factor by correlating the flow conditions, which is the Reynolds number, and the physical roughness of the pipe, which is the relative roughness.
This graphical solution is particularly valuable in turbulent flow regimes where direct equations are more complex.
Alright, so after we get the value of ratio factor, so we can calculate the head loss measure. So since we have two different pipe, so we need to calculate two HL measure, and then we combine it to get two HL measure total. Alright, so we calculate the HL measure by using formula F multiplied by L length over D multiplied by V squared over 2G. So after we calculate the head loss measure, of course we need to calculate the head loss minor also. So formula for head loss minor is KL multiplied by V squared over 2G. So in this case, we have 8 part of head loss minor. So first inlet, elbow 60 degree, elbow 45 degree, pump inlet, pump outlet, 3 elbow 90 degree, gate valve and outlet. So in this case, inlet elbow 60 degree, elbow 45 degree, and pump inlet have a same velocity, and pump outlet elbow 3 elbow 90 degree and gate valve outlet also have a same velocity. So after that we calculate by using this formula, and then we get the value of HL minor. So after we calculate the head loss major and head loss minor, we can find the head pump. So by using the formula of P1 over rho G plus V1 squared over 2G plus Z1 plus HP is equal to P squared over rho G plus V2 squared over 2G plus Z2 plus HL. So after we potong, so we get the HP is equal to Z2 plus HL. So Z2 is H1 plus 10 meter, which is the tank from the ground, and then H2 and HL is equal to HL major plus HL minor. So head pump, we use the formula of head pump is H1 plus 10 meter plus H2 plus HL major plus HL minor. So after we calculate, we get the value of head pump. So after that, we need to calculate the required power. So required power, we use the formula rho G Q head pump. So rho G Q HP. So we only use that formula, and then we get the required power. And for the estimated power pump, we need to estimate the efficiency of pump. So we estimate the efficiency of pump is 87%. So when we estimate that efficiency, so we can find the estimated power pump. So we use the formula power pump is equal to required power over efficiency of pump. So after we calculate, we get the estimated power pump, which is, so in the last part of calculation part is to calculate the net positive suction head, NPSH. So formula of net positive suction head is PS over specific weight plus VS squared over 2G minus PV over specific weight. So in this case, PV at 30 degrees Celsius is equal to 4.24 kPa, and V inlet is 12.63 meter per second. So we need to find the value of PS. So the formula of PS is PATM minus rho G H2, which is the level of water and the darat. So after we calculate the PS, we get the value of PS, which is 98.36 kPa. So after we get all the value, so we can calculate the net positive suction head by using the formula that I said already said. So NPSH is equal to 17.62 meter.
The next part is costing. So the piping system that we have designed have like a few components that we came up with, which is centrifugal pump, water tank, pipes, gate valve, elbows, suction hose, and also fluid valve. All of these components has been chosen based on its durability, quality, and cost, because we want to make the budgets be more affordable and also long-term use. So here is the tables of price quoting that have been listed in the piping system we use. So I will go through one by one of the costing. For the first list of cost is centrifugal pump. So it costs 3,000 ringgit for a 10 power horse pump, and also water tanks for 400 gallons. It costs 655 ringgit, and also for pipe for 1 meter it costs 4 ringgit and 23 cent, which is we need 36 of quantity, which is the total of it is 152 and 28 cent. And also the gate valve, it's cost for 75 ringgit for 1 cent. And also elbows, we have came up with like 3 different elbows, which is 90 degrees, 60 degree, and also 45 degree. For elbow 90 degree, we need to use 3 of them. So per unit, it's cost 34 ringgit 31 cent, which is the total of it is 102 and 93 cent. And also for 60 degree elbow, it costs 22 ringgit 77 cent. Along with the elbow 45 degree, also needs 1 quantity, which is cost 31 ringgit 77 cent. And also suction hose, we need 2 based on the length we use. So per meter, it costs 50 ringgit 29 cents. The total is 30 ringgit 58 cent. Last but not least is float valve with a ball, which used in the water tank. Per unit is 155 ringgit, and also the total amount of the costing price is 4,225 ringgit 43 cent. So this cost is really affordable in the piping system.
So I will continue to the last part of this project report, which is the part of conclusions. So from the conclusion of summary findings for recommended for this project, our finding we get our analysis show that the flow in both the HDPE and PVC suction hose is turbulent, which is normal for such systems. And use the MODI chart, we determine friction factors of 0.009 and 0.014 respectively, leading to major losses of over 8 meters total. Also found that the minor losses due to the elbows and valves were significant, totally nearly 16 meters. This highlights how much directional changes affect system performance. Also, in total, the system requires a pump capable of delivering 35.64 meters of heat. The power needed was calculated as 4.02 kilowatts, and with an available NPSH of 70.72 meters, the system is safe from cavitations. The total cost came to just over Rm 4,200 ringgit, making it an economical and durable setup for using HDPE pipes and PVC fittings. For improvements, we recommend minimizing sharp bends, adding check valve, regular maintenance checks, and planning for future scalability if demand increase. So if demand increase, we need to increase the maintenance also. This project also successfully integrates theoretical knowledge of fluid mechanics with real-world engineering designs, resulting in a functional, efficient, and economically viable water supply system for the FKMP construction site for this faculty. The analytical approach adopted for considering energy equation, flow behavior, head losses, firm requirements, and economic feasibility to ensure reliable operation and serve as a model for similar mechanical engineering application. So that's all from us for explaining this project for piping system to build a faculty mechanical and manufacturing engineering at University Tun Hussein on Malaysia.